an orthonormal basis of L2R. That was the I finished up to this. And in the meantime, I also discussed about that what was the need of why do you start from vector spaces, then you Banach spaces, and then finally you arrived at Riemann spaces, and L2R is an example of Riemann space. And here you have both angles and both are defined, right? And yesterday's lecture, in first lecture of Professor Salwan, he discussed a lot about it, that why theta and not both are required. So when you have both, if you remember, like if you have the orthogonalization process we discussed, so if you have some set of vectors which are linearly independent, then you can create an orthogonal set of vectors from here, right? What was the procedure? Usually defined as usually defined as E1 divided by size of the vector. That is why size is required if you want a unit vector. Then how do you define this E2? So suppose E1 is this vector, then E2 is this vector. Then you want to find out E2. Right? Even if you are linearly independent, but you are looking for orthogonal vectors. Right? So I shall be taking
Live.
so you want V. So from this V1 you have got your E1 which is in the direction of V1, right? Now how to get V2? So you take the projection of V2 log V1, right? And then so by summation of say this is P. So this vector say this is some vector Z maybe. So this Z vector you can write as V2 minus P, right? So this P vector, how do you write the projection? Yesterday I wrote the formula. Maybe before yesterday. How do you write the projection on any vector? Say in R3, P dot B is AB cos theta, right? The projection of A along B is A cos theta, right? So how do you write it? A dot B divided by. So this you can write in terms of inner product, right? Divided by norm of the vector P. So likewise, you can replace P by using this projection formula in terms of inner product and distance. And you know cos theta. So basically, that is why you require angle because you want to get the projection. That is why you are in N2R because both are defined. So this all these discussions we did this way. And then to arrive at the basis of N2R, what did we do? So when you write a basis, that means you are looking for independent directions that are possible. Like in R3, you have only three mutually perpendicular axes. That means three mutually directions are enough to write any vector. When you are in L2, that means it is an infinite dimensional space. How many vectors you require? Infinitely many, right? And to achieve that, what do? You just break it into one. You break it into closed subspaces and so on. Right. is not perfect because Bj means after certain number of iterations you arrive at Bj. So you decompose L2R into subspaces, closed subspaces. And our motive is to generate entire L2 by using a single vector, right? Single vector, one vector only, say I. And in this process, we have defined certain process. I will not write those. I have already written that. So the key assumption was Bj plus 1 you write as Bj plus Wj. Right? And I proved this also that L2R you can write as direct sum of Wj where J is in Z. We discussed both of this. And say this is from J. Bj is a closed subspace. You want to have a larger space. That means how to get a larger space from a given space. From say x-axis, if you want to have a say x-axis is 1D, right? One-dimensional space. If you want to add some new vector in this which is not in that, then what you should do? You should add a vector. You take a vector which is actually in a different direction. So mutually perpendicular vector is the best suitable direction. It is easy to deal with. That is why you take another vector is mutually perpendicular to x-axis, that is y-axis. Then you get any vector in R square. If you have another vector mutually perpendicular to both of the vectors, then you get R3. Likewise. So suppose Bj is of some space. You want to add some new vector which is not in this Bj. Then only you get Bj plus 1. So for that what we do? We add vectors which are basically orthogonal complement of Bj in Bj plus 1. So all the vectors in Wj they are orthogonal. So what was the definition of Wj? Wj is defined as say it contains vectors in Bj plus 1 such that B is orthogonal to Bj, right? So this Wj is actually orthogonal complement of Bj in Bj plus 1. And you keep doing it. Further you add say Wj plus 1, then you arrive at your Bj plus 1, Bj plus 2, likewise. So this also I have already discussed that if you wish to write a vector in L2R, how do you write a vector in R3? Any vector, how do you write? Suppose a vector is in R3, how do you write this vector? In terms of unit vectors? Three different directions. Basically you take projections of B along ijk. So how do you write the projection? This will give you the component and then you multiply by it. And then same thing you do again. Right? Likewise. So if how do you write this vector? You need to, so basically this is the projection of the vector along x-axis, projection of the vector along y-axis and so on. So likewise, you take the projection of f along wj. By this expression, what does it mean? Every function here I can write as direct sum of vectors in wj. So I can write this vector as say, f I can write as summation fj where j is in j. Because you have infinite dimensional space, these wj's are infinite in number, so you have to take projection of f along each of wj's, you can get your vector, you can reconstruct your vector. All these are from my previous class only. Now the question is how to write these fj's. So fj is in wj, right? Fj is in wj. So you want a basis of, you are looking for an orthonormal basis of Wj. So one of the points of MRI says that if f is in Vj, then f of 2x will be in Vj plus 1. What was the reason behind this definition? What was the reason? Because I want to write every element of each of the Wj by a single vector. If I know a vector in V0, I know the vectors in V minus 1, I know the vector in V2, V1 also. Right? This is the reason. So this, and then one of the properties of MI, that it says there exists a function for phi in V0. What was the name of this function? आपको याद हो जाना चाहिए. Scaling function. Also I referred as father wavelet, right? Father wavelet. So one of the properties of MRI says that there exists a function for phi V0 such that, and this function is in L2 such that what happens? X minus k is in where k is in, right? So this is a property of MRI. Like in this, there exists a function phi V0 such that this is an ONB of orthonormal basis of V0. Right? So if you combine these two, from there what will happen? If I multiply, so this is what phi x. So if I multiply by for jx, it will be Vj because of this property. Right? This is in V0. So every time you keep multiplying by 2, you will be moving to x space. So this will be in Vj, and by this property what will happen? So if this is in V0, then this is on orthonormal basis. So what will happen? And see, this is an orthonormal basis, this is also in V0. So all these vectors will be in Vj, and because this is an orthonormal basis, this will be an orthonormal basis. ONB of Vj is an orthonormal basis of Vj. We have discussed this, right? So if we know orthonormal, for normalization I need to for normalization means norm 1 of the vector, I need to multiply. So if I know the basis of each of the Vj, I know the basis of L2R. Why? Because union of Vj's is equal to L2R. One of the postulates of properties of MRI. Now, so where is psi? That is the question, right? So psi is, so by the construction, how did we? So if you are in Vj, how did we get our Vj plus 1? We add its orthogonal complement. Wj's are defined as Vj plus 1 minus Vj, or Vj plus 1 equals to Vj orthogonal complement. Right. So if I know a vector in phi is in V0, I know vector. I know the scaling function. I know the basis of V0. I want to now find out what is there in W0. What is there in W0? So I need a vector in which is orthogonal complement of this phi in V1. So I am looking. So if any vector is orthogonal complement of phi, that will be in W0 actually. Any vector which is orthogonal to this phi, that will be W0. So this relationship is very crucial actually, and W0 is in phi. W0 is in and V naught and W naught, they are orthogonal. Right? I know the basis of V naught. What is the basis of V naught? If I know the scaling function, this is in V naught, then MRA says that this is orthonormal basis of V naught as per MRA. So if I know this scaling function such that this is an orthonormal basis of V naught, then I can get our W naught. I need a vector which is orthogonal to right, and because of this property that fx is in V naught, then what will happen? F of 2x will be in V1, right? F of 2x will be in V1. So if psi work phi is in W naught, by this property, what is in V1? This will be in V1, right? And because of this what will happen? This is orthonormal basis of V naught. So immediately, if you substitute x by 2 to the power 2 into t, if you substitute, you can immediately prove that by using this, you can immediately prove that under root 2 work phi 2x minus k belongs to z is OND of P1. Very easy. If you know this, just replace in the integration x by 2t, you can easily prove it that this will be orthogonal basis of V1. So where is V naught? V naught is this. You have V1. So work phi is here, right? Work phi x. Work phi 2x is in V1. Where are work phi 2x minus k? They are in V1. If work phi is in V naught, it will be in V1 also, obviously, because V naught is a subspace. So, if work phi is in V naught, this will be in V1 also, right? Because V naught is the subspace of V1, and this is the basis of V1. So, any vector in V1 I can write as, what is the meaning of basis? Any vector in that space you can write as a linear combination. So, I can write work phi x as, because this is where you are going to get your filters. So I can write this as hk under root 2 work phi 2x minus k. K belongs to z. This is the orthonormal basis. Then how do you get the elements of the basis? K 1, 2, 3. K minus 1, minus 2, minus 3. Right? This equation has a name. This is not scaling equation. Because dilation equation, also so this equation is a name, that is called dilation equation, and also I think it is scaling equation also. Dilation equation. Where is psi now? Tell me, where is psi? Work phi is here. Where is your psi? Whatever discussion I did. I am looking for new directions which can generate our V1. So I am looking for a vector here which is your psi, which is orthogonal to this work phi, right? So I am looking for a vector which is orthogonal to work phi, and this psi is in V1, right? And I know the basis of V1, so I can write psi also, right or not? I can write. So I write psi as with new coefficients gk. K belongs to z under root 2 work phi. Work phi 2x minus k. Right? So if I know MRA, I know work phi, I know this basis. So basically psi is your wavelet. Psi is your wavelet. So you can generate your wavelet, if you know what phi, you can generate your wavelet by the series. Right? If you know GKs. If you know your GKs, you can get your wavelet. So I got two equations. Is that both equations are clear? I got two equations. One equation I got because 1 phi x is in V naught and it is in V1 also, and I know the basis of V1, so I can write this equation. Very simple. Because 1 phi is in V1 and I know the basis of V1, I can write this. I can write this also because I am so. What is the property of psi? Psi is actually orthogonal to 1 phi. So I am looking for this type of these type of vectors. GK is new coefficients, but the basis is same. So this is your order wavelet or scaling function, and this is your other wavelet. Also simply sometimes known only referred as wavelet. Wavelet means mother wavelet also. Generally. Now, uh, when I wrote in the beginning of I wrote the Fourier series, I wrote minus and 12. But I said there can be anything, right? So here the discussions that I am doing from the book, they are taking one PID function. So that means 2L is 1. Right? So finally this I will be using this formula for that. F x exponential 2 pi I x x. I will be using this formula. Right? So if you take so now I'll be doing the calculation, right? If you take Fourier transform of this entire expression, that means you multiply by this expression, exponential term, and integrate it from 0 to 1. So after some calculations, from here you will be getting this 1 pi cap xi h xi by 2. This is a new function. I need to define what do I mean for this. 1 pi. So this is the dilation equation, and this is the dilation equation on the Fourier side. When you take Fourier transform. What is capital H here? If you take the Fourier transform, do some calculation, and you assume h xi to be of this type. 1 by under root 2 hk exponential 2 pi I xi k belongs to this. Learning is another thing. This is the Fourier coefficient, AN's actually, and this is the Fourier series. HKs are so when you after putting this value, so after integrating both sides multiplied by this, you assume your xi to be this. So you get an expression. If you replace xi by 2, whatever you get here, you get here, right? So you need to assume this, then you get this expression. And what is xi? This xi is nothing but Fourier series. Whose Fourier coefficients are hk. And this is the function. So basically, this is if you compare it with Fourier series, this is fx, and this is an a naught plus a1 something like that is written on. So this is called this small hk called low pass filter coefficients. And this capital H is called low pass filter. मुझे कंफ्यूज करोगे तो पूरी क्लास कंफ्यूज है. So this, so how do you get this low pass? This equation is clear. Take Fourier transform. You arrive at this. You arrive at this definition. This capital is called mathematics. You can do. This is not a problem. Now, how do you get the G case? Right. So for G case to, if you want to get G case, then you have to satisfy this condition. Okay. If you satisfy this condition, you get a relationship between. So you take inner product of this. How do you say the two vectors are orthogonal? Inner Hilbert spaces. You take inner product similar to the dot product in R3, then it should be equal to 0. So you take inner product of this spaces and then equate it to 0. You get a relationship between HK and GK. Right? So if you do this, so your I need to get a relationship between HK. I know HK, suppose, then I need to get GK. So for that I take because how to get psi? Psi is orthogonal to every vector in V naught. Psi is orthogonal to every vector in V naught. What types of vectors in V naught? This type. So that should be 0 for every k. Right? If you do this, I'll write it in short that finally you get this kind of equation. You get this kind of equation. H G K H K minus 2n and you get k belongs to z 0 for every. So after doing the inner product, you get a relationship between GK and HK. And if you solve this, this will give you an expression for GK in terms of HK. Right? Calculations you can do. Finally, you will get this kind of relationship. This is not, I have to write it correct, otherwise it will go 1 minus k. It will give us this kind of equation. These GKs are called high pass filter. Right? And how do you, so like capital H, you can define your capital G also. How do you define? Capital G exactly 1 by under root 2 exponential 2 pi r xi k belongs to z. So GKs are defined by this equation, similar equation. So you can also prove that H and G they satisfy this. This is called quadrature mirror filter. Quadrature mirror filter. The equation has a name. Right. And then G xi can be defined as exponential 2 pi I xi. So they are related actually. They are related. Right. So if you know H, you know G. So you can write capital G in terms of H. The expression is like this. Why the mirror term is coming? See, if you know some, so basically they are complex values. Huh? If you know H, So what is the relationship between H and G? You are writing G in terms of conjugate of H. So if you know any complex number, where is the conjugate? A plus IB, you know where is the conjugate?
नीचे
Mirror, na?
Mirror.
That is why this mirror is used. What is a mirror filter?
Sir, why is your HK lower suffix has been changed to lower suffix of HK minus 2n has been in the summation.
करना पड़ेगा.
So
So you
why?
have to write, you put it here, right? You put both expressions here one by one. You have two series, na?
Yes, sir.
First put this and then put this. Do the calculation.
ऑप्शन को स्किप करो
तो समराइज कर देते हैं अभी तक जो क्या क्या किया. So we were trying to form a basis domain. In that process, we had a work file which is in V naught, and then we defined a size which is W naught. And what is the relation between all this? They are related like this, direct sum. Right? Then I wrote work file as a series, right? And I wrote this psi also as a series, right? Something is here only. All these are written. Then from here I got this relationship between. So here you have H case, here you have G case. Right? They are actually orthogonal to each other, and from there you got this equation. G K H K minus 2 belongs to Z 0. From here you got this that G K is equal to minus 1 to the power K minus 1 minus K. इसको ठीक है ना? So this small h is called low pass filter coefficient. Capital small g is called high pass filter coefficient. And there are some relationships also. There are two. H and D they together satisfy this, right? So if actually H0 is 1, this can be proved by using this condition. Our scaling function shall be satisfying everything properly. Mean by theorem of integrals. Right? So basically, from this condition, it can be proved that H0 is 1. Right? And what is, when you write the expression for H, what is xi? What is xi? H is 1 by exponential 2 pi I k xi. So this xi is actually your xi is the parameter that appears in your back color. So this xi is a frequency. Xi is representing frequency, right? So xi0 is what? This can be proved by using this. 0 is 1. So xi0 is what? Frequency is 0. 0, right? So frequency 0 means it is related with signal with low frequency. Right? So H01, if H0 is 1, what will happen to G0? H0 is 1, G0 will be
0
See this equation. This is true for this is true for every line, almost everywhere. So you can put this. So this is called your low pass filter. What is the reason? Because when the frequency is low, it gives a non-zero value, and this gives you zero value, right? So if you pass the signal, it will be remain and it will be removed. Because for this the filter coefficient will be zero. So this is called low pass because it will pass low frequencies. High frequencies, this is called for the reverse. Actually, if you so from this there is another equation I wrote now. This plus minus r equals to 1. Right. So if you put h0 here, then you'll be getting h plus minus r equals to 0. So if the frequencies are higher, so h will only pass low frequencies, high frequency will be 0. For g, this will be 0, but it will pass high frequencies. Reverse. Right. If you remember the lecture of Dr. Udit, what he was studying, suppose you have a signal, right? Signal is like this, like this. But when we try to analyze the signal, we take only discrete values. You remember that we took dots, right? So let us take first continuous.
थोड़ा सा बोतल को साइड कीजिए
So I try x.
रिकॉर्डिंग कर रहे हैं
So suppose xt is some signal, right? And then if you take the Fourier transform, what will happen? This is the signal. You take the Fourier transform. What will happen? It tells you that okay, these are the frequencies present. You have seen the graphs, right? By which frequency signals it is made up of. Now, what you are looking for? You want to filter smaller frequencies. So for that, what you should do? Multiply by
कट करके चालू करो
multiply by this.
बड़ा वीडियो नहीं जाए